Welcome again to the NPTEL course on storage systems. Last time we were looking at some aspects of the ZFS file system. I will just elaborate it a bit more today and then continue with some discussion about how redundancy mechanisms can help you in handling the kinds of errors that typically are present in file systems on storage devices. So, again just to recapitulate, the ZFS design has a user level and a kernel level. At the user level, you have the POSIX interface, the ZFS interface, essentially the file system interface. Because this is a combined design of both, it is a file system and a volume manager together. It also can provide certain devices from the storage pool, multiple disks are there. So, you can provide some block devices. So, you can directly access some of those things. Okay. And there are some, in any complex system there is always what is called a management interface. Management interface by which you can manage the device. If it is complex, it requires management. So, it turns out you can either have a GUI based management interface, or you can have a management interface through a program like written in C language, for example, right. And the way you access the functionality of the basic primitives of management is by, there is a library called libzfs, and this is what you include, and then you get some functionality with it. It defines certain data structures and functionalities with it. For example, you have the ability to manage it using this management interface 1M, that is zpool and ZFS. Things for example, in ZFS are you can create a file system, delete a file system, mount a file system. These are all high level management operations. Similar in a pool also, you can add something to a pool, remove something from a pool. Okay. These are all storage devices. For example, I had a new disk, I want to add to it. Okay. So, these are the kind of things that you can do here. Okay. So, the most important thing to remember is that in any complex system there has to be a management interface. That is the only way we can interact with it to set it up for the way we want to use it. Okay. Without that, it is actually useless. Okay. That is why it always is, if you think carefully, there has to be a management interface. Now, finally, these are the user level, then there is a kernel level, and I think we saw the picture last time. It is this kind of detailed diagram, and I went through a bit of it last time. I will just add a few more comments as we look at it one more time. Okay. So, as I mentioned, these are the consumers on the top, and this is the functionality packaged into a library for management purposes. Okay. So, this is the management side of it, this is the actual use side of it. Okay. So, this libzfs in turn uses some internal device names. The reason why you need all this stuff is because this particular system has an ability to do what is called snapshots and clones and other things. So, the snapshots and clones also can be seen as different devices. These are all internal devices and they are named using this particular interface. This, so for example, if you have a particular clone, it is identical to some other let us say version of the file system at a particular point in time, and I can do what is called a write clone. That means I have an exact copy of the file system as it existed at a particular point in time, and I want to be able to write to it. Now, that will be given as a new device, and then on top of the device I will have the regular file system structures on top of it. So, now when I write to it, it will go through that particular the regular file system call, but it will actually use this device. Okay. So, essentially what this does is it gives you some multiple internal names in the kernel, which can be used to access snapshots, clones and other kinds of, let us say, point in time versions of your file system. Okay. You need to be able to name them, you need to be able to access them, you need to be able to manage them. That is why all this stuff is sitting on this side. Okay. So, for example, I can take a snapshot of my file system and then I can later say that I don't need that snapshot, or I can later say that there is a snapshot, I want to access a particular file because I accidentally deleted it in my regular directory, I want to access it, right. So, when I want to do it, it may be that I need a mounting operation, I need to be able to mount that file system, okay. So, I need to have some kind of capabilities of naming them, accessing them, managing them. So, all this functionality is exported through libzfs at this point, but also through some device names, okay. And the traversal is basically, I can have a snapshot of a snapshot of a snapshot, or I can have a, let us say, a version of my file system as of last year. I want to keep it intact, and then I modify something there, that's a new version. I can take a snapshot of that one, and then I can take a snapshot later of some modified things. I can have a, so I need to be able to find or traverse and find out which is the, if I talk about a file, is it the unmodified file of the 2 years back, or is it something which has been modified after I took a snapshot, or after that, okay. So, I need to be able to traverse those files. So, that's where the traversal comes into picture, okay. So, okay. So, let's look at, so I already mentioned about zvol is basically, this part actually is basically nothing more than the regular file system that we know about, okay. It has got the read, write, open, all those usual things, okay. Regular POSIX schematics, okay. Then zvol is a thing which gives you certain devices, because you can see there's a lot of devices out here. Some of the devices, normally what happens in a regular storage system with separation of volume manager and file system is that you talk to the volume manager and say, give me some raw devices. Here, since it's an integrated system, they are providing the capability by which you say certain portions I want to access it directly, okay, as a raw device, okay, as a block device, and that's what this zvol is able to do, okay. Again, Linux, for example, you can have there's something called MD, right, and if you give it some devices like /dev / SDA1, SDA2, okay, it will provide you with a concatenated device, okay, of which you can use part of it for mounting a file system and rest of it can be used by partitioning it. I can use it as a separate device which can be accessed in the using a raw interface without going to block interface, okay. So, those kind of things are also possible here, except that all of this is pulled into one single infrastructure, right. Now, I think I already mentioned ZAP is basically the way in which you want to provide some ability to incorporate directories in the system. Basically, I have a way of mapping names to certain objects, okay. That is what this ZAP is attribute for. Basically, you want to talk about mappings, okay. That mappings is basically this ZAP, okay. And this had to be transactionally done, because you know that when I create a file or create a directory, it touches multiple places on the disk, right. So, it has to be transactionally. So, that is why this is the transactional unit, okay. The ZIL comes in because oftentimes what happens is that databases want something to be, as soon as I finish writing or reading, they want that update of your account or whatever transaction you have done to be immediately made persistent. You can't wait for it to be left in memory and risk the chance of loss in case there is a power failure or things of that kind. So, you want something which as soon as the read or write finishes, especially write, you want it to be committed to disk immediately. So, that is that part of it here. This part of it is basically the thing which is an intent log which is forced to disk immediately. That is why these things, some of these structures can be sitting in memory and they will be drained out through the cache to the actual storage infrastructure, okay. In case you can't afford to wait for it to be drained out through normal mechanisms of flushing, okay, then you want a direct path from here to here, okay. These are direct paths, so that I know that it has to be made persistent. I am waiting, essentially I am doing synchronous reads or writes. So, I want to send out the updates, I commit, I do transactions and then I log it into the intent log, Okay. So, now once it is in intent log, it is essentially persistent. I might lose power, etc., but the intent log keeps track of the transaction, and in case something bad happens, I can recover from the log. That is why the ZIL is here. The good thing about this also is that the ZIL, since it is a log, I can put different types of devices more suited to logging purposes. For example, nowadays flash is coming in. If you have enterprise flash, you can do lot more IO operations by incorporating some amount of flash here. Okay. So, this is separate. So, this is a logging device which is separate, which can be separate from a regular disks which are out here. Okay. So, so this is I think I mentioned the data set and snapshot, all those functionalities, traversing, all those things are available out here. Okay. So, if you want to do a copy and write, essential write, we have to figure out this will interact with again the transactional layer. This is the transaction layer. It will interact with it so that it will do the copy and write. Okay. All those things are out here. The copy and write part of when you update something, etc., all those things are again have to be done through transactions. Okay. Because finally, what you have to do is when you do copy and write, you are going to create a new object which has the same set of objects as the previous version, except modified in one or two places where you made the copy and write, right. So, that means that this again is not a atomic operation. It's not, it cannot be done atomically on a disk. That means you have to do a transaction for that also. Okay. That is why this stuff actually depends on the transaction unit. Okay. And that when I mention transaction units, all these things are typically first done in a memory log. Okay. You have it in memory log and then you try to drain it out. Okay. Because you want to batch it. Again, you are talking about disks which are very slow. So, you can't do it every time you want to, you can't push out transactions immediately, because if you do it, then you have to suffer the latency of the disk. So, what you want to do is to keep the memory based transactions and drain them out by doing clustering. Okay. And then once they make it to the home locations, then you can release the space on the log. Okay. That's basically the idea. Okay. That's a standard. So basically this is the part which actually does all the logging in memory, and then this is being cached here. This is what is called an adaptive replacement cache. This is slightly let's say modified version of regular buffer cache. Basically what happens in a buffer cache is that it usually tries to optimize with respect to LRU, okay, least recently used blocks. Now it turns out that oftentimes LRU is not useful if you have streaming workloads. So you want to be able to figure out how to apportion the amount of buffer space that is available to LRU kind of workloads and to streaming workloads. So that is why this is an adaptive model which will look at the way it has certain self-correcting abilities. It looks at the kinds of misses that are taking place and then decides that this is closer to a streaming workload and then gives it more space for streaming. This basically in some sense it has a notion of current available let us say space for streaming versus LRU kind of workloads, and then it essentially simulates what would happen if I have slightly extra space this way or that way. Depending on the losses, it can figure out that okay, this whatever is coming in should be given slightly more streaming buffer space rather than what is currently possible. So it actually has a self-correcting ability. Okay, that's what is ARC. Okay. Now once you are in the ARC, this is basically the caching sub layer, and then you have to, so often you will be flushing it to disk. Okay, and that is where the ZIO pipeline comes into picture. Okay, and this intent log also is connected to this, because if you want to flush anything to disk immediately, you can go through this. If there is some reason by which you have to really make it sit in disk, as I mentioned, this is already logged here. Okay, but if you want to make it flush the log so that actually resides in home locations, actually it's where it should I finally be, then this can directly go from here to this side. okay, because this has got the reason why you can see there are multiple entry points to ZI pipeline. Some of it can come like this, or some of it can go through all these things and come here. Okay. And okay, so now notice that there is also some other complication that occur here. You will notice that you might also have some redundancy management going on. That is, I might have what is called RAID 1, that is mirroring, or RAID 5 and that kinds of things. And that also all these are managed out here. I will come to that soon. Okay, I will just talk a bit about this, but basically the important thing to notice is that at this point in time everything is a virtual block, because basically what does for example, let us say the file system is what we are using, right. It thinks that it has got a block device, okay, and this block device is of some arbitrary size and with arbitrary reliability properties. Okay. That means it can have it has been replicated 3 times or replicated twice, or it has got a particular type of redundancy. That is abstract notion that a file system has got. Okay. So, the file system basically just knows that it is writing onto a block device, and the redundancy part is being handled by somebody else, but it and that part of it is being done by this part. Okay. So, when since it has got only the notion of an abstract device, this device actually could be pieced together with lots of disks out here, lots of disks. For example, there could be 100 disks out here. Okay. And somebody has carved out of this 100 disks some 1 terabyte block device, for example, or something of that kind. Okay. And then that 1 terabyte disk itself could be mirrored, or it could be in RAID 5 configuration, RAID 6 configuration. Okay. So, what we have is certain virtual devices which have internal structure. This virtual device itself could be coming from multiple physical devices, and the virtual device itself could be mirrored, and it could be spanning 2 disks. Okay. So, to make all this reasonably easy to do, they have the notion of a virtual device, and then there is some kind of a tree-like structure by which you will say that this virtual device is composed of this part of this 1 terabyte disk and this part of this other 1 terabyte disk, and this itself is going to be mirrored. Okay, I get some amount of disk space by combining these two, and I am giving you some mirrored capability. That means that half the thing is here and half the thing is here. Okay, in terms of one half of the mirror is this side and one half of the mirror is this side, or combination of this. Okay. All these things are left open to the device configuration through the management interface. Okay, through this. Okay. So, at this point in time, the VDEV basically what it does is it translates whatever things that have to be written, it goes through all this multiple levels indirection, figures out exactly which device it is actually talking about, because it could be that it is the virtual device that we have is concatenated from 2 terabyte disks, and then that device itself is for redundancy purposes is going through mirroring, and that means that it is using for mirroring purposes it is using some part from this disk and some part from this disk, or combination of various parts here and there. So, somebody has to map what this guy is talking about to which parts of the disk we are talking about. That is what all this is done here. Okay. And then once it is done, then you can do the actual I/O operation. This is basically the actual device delivery. Okay. So, again I will just run through it one more time just to make sure it is clear. So, the Z-wall is basically presents a raw device, okay, and it is backed by specific storage pool, multiple disks out there. Data management unit is basically, it is a transactional, it provides a transactional model, okay. The flat address space we are talking about is basically all the devices that are available. Okay. For example, in Linux, it will be the standard /dev SDA1, SDA2, SDA3 without a memory, without a volume manager, okay, whatever the devices are. Okay. And the consumers, the guys upstairs guys, okay, interact with DMA by collections of objects and transactions, okay, sets of objects and transactions. So a transaction is basically a set of operations that must be communicated to disk as a group. Okay. So as I mentioned to you, the snapshot layer basically depends on a base file system to get its space, and it adds a certain other additional copy on write objects, right. So there is a hierarchy that is there now, because we can say that one snapshot is based on one file system, and this snapshot itself could actually support some other later snapshots, okay. So there is a hierarchy of namespace, okay, and there could be some inherited properties, okay, with respect to, for example, most file systems, if my snapshot would have a lot of the same facilities as the previous one. It might, for example, I might mount this particular file system in a particular way, probably the snapshot thing also will have the same kind of parameters. Okay. It's very unlikely that I have a file which I am doing, let us say, I am doing what is called data and metadata logging, but the snapshot thing I will only do metadata logging. Usually that doesn't happen. Okay. If you are doing snapshot, typically all the things that I have snapshot have the same property. That's why there are inherited properties. Okay. Okay. And similarly, there are all these usual things about quota and management also rolled in at this point. Okay. As I mentioned earlier, ZFS is basically a way to create name object associations. Okay. That's how they implement directories, and they use it for also keeping track of information about the pool-wide properties, because various different pools might have different attributes. For example, one set of pool might have read1 attribute, some other pool objects together might have read5 attribute or whatever. Okay. So all those things are also here. Okay. And as I mentioned to you, there is an intent log, which basically is specifically tailored for databases. For when you want to make the data synchronously resident on the disk, you have to log it. The data is going to be logged into this part, so it's not lost in spite of whatever happens. Okay. And this will be finally, since it's already logged, it can be sent through, this will interact later with the regular ZIO mechanism, so that it finally goes and to the home locations. Okay. And this is basically, the traversal part is basically a way to go through multiple versions of clones and snapshots, for example. Okay. So all this is being supported on a single pool of storage. Okay. So you need to have some way of traversing these things. Okay. So it also helps you to do what's resilvering. Is basically you have a mirror, one mirror fails, then it is called resilvering to copy it from the existing, the remaining remaining copy. You want to copy it onto the new set of disks that are going to take its place. Okay. It's called resilvering. Okay. Scrubbing is one in which usually what happens is that if you look at certain large numbers of disks, if you don't keep accessing it, sometimes there are some errors called latent sector errors that can develop. So what you want to do is to every so often keep reading them, and then in case you are not able to read them, then you use your standard error correction mechanisms to rebuild it again. If you don't do this, the time when you want it, it may be that you want it at a time when you are already in an error situation. You are already in an error situation, and then you are trying to read it, and then it comes back and says this is an error. Okay. At that point, you can't do anything, because you don't have access to data which is used for fixing the problem, because you cannot read it. Okay. So to avoid the situation, you preferably try to keep reading all the disks every so often, hopefully in non-error situations, so that if there is some problem reading a disk, the standard error mechanisms for recovery will be available. Okay. That's the idea. Okay. So yeah. So there are various other, the traverser also gives you some other powerful capabilities. If you want to find out what all has changed within a particular period of time, you can do it, because usually there is a copy on write with respect to snapshots and clones, etc. So, because of this we are able to figure out what is the modified state right now without too much trouble. Sometimes that is important for backup purposes, or if you want to restart something, you want to know what has changed. Okay? So, the traversal mechanism, because of the copy and write nature, it allows you to do some of these things quite quickly. I think I already mentioned about this, basically the storage pool allocator, which is basically the third part. Okay, if you look at the thing, this is the whole, all this stuff is basically that. Okay, this is the cache I already mentioned. This pipeline, basically it turns out there are lots of phases that an I/O operation must go through. For example, you might have encryption, or you might have compression, or you also might want to do checksumming, because you want to check whether the data is actually valid, right. So, what they have done here is to provide a pipeline by which all the operations go through, just like a in a machine. You have a pipelining in the machine. We also have a pipelining of operations out here. Okay. So, I think I am not sure it is very clear, but basically you might find, for example, compression is one phase, checksum is another phase, okay. Actual I/O is one phase. Okay. For example, you have a write here, you might want to open the device, it may be that the I/O is multiple children, okay, because one I/O might be composed of multiple sub I/Os. So, you want to wait for all the I/Os to be completely processed for issuing it out. Okay, that is what this is. You might want to compress all of them. Okay, you want to, because you are doing compression, for example, or encryption, and then you want to generate it, because you are writing it, you might want to checksum, because you want to write the checksum. As I mentioned in the ZFS, there is a checksum that is kept as part of metadata away from where the data is, right. So, that you can check whether the metadata, the checksum that is kept to the metadata, it is the same as what is there in the data. And since there are two separate places on the disk, hopefully one error cannot actually correct both of them. So, this also has to be done, and this is required in case an I/O is you do not find enough space in a single disk, for example. Okay, you have to get some spaces from multiple areas. So, there is a big I/O I want to do, not everything is available in one single place. So, I have multiple sub I/Os, I have to split it, okay, so that I get some space from here, some space from here, some space from there. Okay. So, that is what the gangs are basically. Okay. One I/O becomes multiple gangs, and this is basically the part which does things like finally I have to do the allocation, because when I am writing to it, because this, remember that most of the system is basically does not do any write in place. Okay. Since there is no write in place going on here, you have to essentially allocate new places where it is going to go. Okay. That is why all this stuff about allocation is there, okay, whenever you are doing a write. Okay. And then after that, you have to do the actual I/Os, and you wait for all the children to be done. Because I am simplifying it a bit too much. This is for write. You can see anytime there is a write, right, all these things are going on. Okay. This is not part of the write, so do not forget about it. This is part of the write. Okay. This is part of the write. Okay. Whereas if you want to do a read only, you start from here, it is open. The read also might be composed of multiple sub I/Os. Then there is no R here, so you wait for all the children to get ready, they become ready. Now you can start reading all the I/Os, then wait for all the children to be finished, all the sub I/Os to be finished. You verify the checksum, okay, and then in case it may be that you may need to decompress it, because the read also could be compressed, I have to decompress it. Okay. So the read logic will be slightly different, okay, than from the, for example, the read logic will basically go from open the device, wait for children to be ready, do the decompression, verify the checksum, and then you can, in case there are multiple subreads you have to do, you have to pick each of those things and then check the checksum for each one of those things. Okay. So, there are multiple phases and each of these reads, writes actually go through those phases. Okay. That is basically the way they have done it. Okay. So, again, one important thing it has to do is to take this virtual block addresses and convert it into actual physical locations. That translation has to be done here. Okay. And in case there is the VDEV finally is a thing that handles whether it is mirroring or RAID, etc. Okay. So, this is the part which we will go into that a bit in detail soon. Okay. And this is the thing which actually does the physical devices, or it may be that your file system actually is built on top of some other files. Okay. Then it has to go through the VFS interface. For example, you might have things like loop devices, then we will do this. Okay. So, now let us look at one interesting thing that ZFS does. Okay. So, for this we have to understand something about RAID file. Okay. So, I think before I go it, let me just go slightly further ahead and then try to look at types of disk redundancy. Now, there are two types of models. One is called the MDS model and the non-MDS model. Okay. In the MDS model, it is basically you can handle a certain number of failures. It does not matter which type of failure, which disk fail, etc. It is uniform. Okay. Any 2 disk fail I can handle it, or any 3 disk fail I can handle it, things of that type. Okay. This mostly that kind of model. Here basically there is some specificity with respect to if 2 disks D1 and D3 fail, then I can handle it possibly, but sometimes I am not able to handle some other 2 disks failing. Okay. Basically because the way the parity is computed is done through a certain they are done by using certain combinations, and in some combinations you can recover from it, in some combinations you cannot recover from it, okay, of the types of failures. Okay. So, this is the one which is most popular because you are guaranteed that any 2 errors can be handled, whereas here it may be not possible in some cases. For example, 3 errors are there, not all 3 errors can be handled, some 3 errors can be handled, but some 3 errors may not be able to handle. Okay. So, of the MDS these things are quite popular, okay. RAID 1, RAID 4 and RAID 5 and RAID 6. Okay. RAID 6 is just about being used, but these things are used quite a bit. What is RAID 1? RAID 1 is basically mirroring. That means you have a piece of data, you have another copy of it on a different disk. Okay. Now, you can ask yourself, how much is it being copied? Is it at a bit level? Is it at a byte level, word level? Is it at the block level? Okay. Normally, when we talk about disks, we try to do at a block level. Typically, it is 4 kilobyte or something like 8 kilobytes, etc. Okay. So, when you are doing mirroring, that means that I am doing at the block level. Okay. So, basically, I have 4 kilobytes I have written onto one disk. I make sure that the same 4 kilobyte information is also written to another disk. So, in case one fails, I can figure out from the other one. Now, one thing one should remember in the case of memory versus disk is the difference that in memory when it fails, you can't figure out, it is not self-describing in terms of where the failure is. Because when a memory fails, it is a very simple device, it cannot tell you that I failed in some sense. Whereas a disk will tell you that there is some additional information basically because you go through a certain sophisticated protocol. If you are not able to read it, it will tell you that I can't read you, I can't give you, it gives some information back. Okay. There is some level of additional information saying that I failed. The memory can, for example, can give arbitrarily wrong information, it will not tell you that it did something wrong. That is why it turns out, if you look at these kind of systems, if there is a single failure, I can figure it out that which disk actually failed, and then I can use parity, for example, to fix a problem. In memory based systems, if there is I have a parity, a single parity, if there is if the memory is gone bad, okay, all I can know is that the memory is gone bad, I cannot fix it, okay. Whereas in disks, because the disk tells you that I went bad, okay, therefore I know how to fix it, okay. Memory does not have that capability. That is why if you might have heard about ECC. ECC is basically error correcting and error correcting code, yeah. Error correcting code, okay, ECC, right. So you notice that unless you have with a single parity, it can't do it. Okay, you need at least 2 bits. Okay, so without 2 bits, there is no way to do correction. Whereas with the disk, we just do parity and you can correct yourself. Okay, the difference being, of course, as I mentioned already, because in some sense, disks, because of the complicated gadgets they have some self-description capability with respect to error reporting. They will tell you very clearly I have failed. Okay. Memories do not have that capability. Okay. That is why you need ECC for correcting code. Parity is not enough. Here parity is enough. Okay. So RAID 1 is basically mirroring, and there is also other varieties. RAID 2 uses something called Hamming code, the regular Hamming code, which also is used in memories. Basically, you take disjoint sets of bits, usually 2 to the power of I, for example, where I equal to 0, 1, 2, 3, etc., and then have a parity for all those things, and then you can essentially figure out where the error, because depending on which parity is not working out, you can figure out where it actually failed. That is the basis of ECC essentially. Okay. Now RAID 2 also can do similar things. Okay. You can use Hamming code here, and typically it is done at the bit level. Okay. So RAID 3 also is at the level of word, at the word level, and these things require what you might call synchronized disk spindles. Means suppose you want very high speed, extremely high speed access to disks, then you can take multiple disks and then synchronize the speeds at which they are running. They synchronized, completely synchronized. So if you read one bit from here, you can read a corresponding bit from the other disk at the same time. So then you will essentially get, if you have 10 disks or let us say 16 disks, you are essentially getting 16 bits every let us say bit time. Okay. 16 bits you are getting it. Okay. So you can do it, but the problem typically is that getting these 16 disks or 8 disks or 4 disks properly synchronized is a very tricky business. It has been done. In the past, it was done in the early 80s, it was done because disk was slow, and for doing some critical things, you needed that speed, and you take the trouble of synchronizing the spindles, disk spindles, and you would get 4x improvement in throughput, etc. Okay. So, but nowadays almost nobody does it. Okay. There are still possibly some very demanding applications where synchronized spindles are worth the trouble, but generally nobody uses it. Okay. So that is why RAID 2 and RAID 3 are not used. Okay. RAID 4 is used not very commonly, but there are specific designs like NetApp's design where RAID 4 makes sense for them. I will come to that also. Okay. They use RAID 4. Okay. RAID 5 is the one which is widely used if RAID 1 is not being used. Okay. Typically RAID 1, RAID 5 are the typical choices. Okay. And many motherboards or RAID disk controllers, they support RAID 1, RAID 5 typically. Okay. There is also something called RAID 0, which is not a redundancy model, it is basically a concatenating model. It basically takes 2 disks and gives a bigger combined virtual disk. Okay. So RAID 0 is not really a redundancy model. Okay. So you have so RAID 4 and RAID 5, basically RAID 5 what happens is that you take a few number of disks and then compute the parity and store it on the other side. But if you do it for all the blocks, then the parity is going to be used all the time, the parity disk, because for every write you have to keep on accessing the parity disk, right. So it turns out that the parity disk could be a bottleneck, because the parity, say any access anywhere, you have to, for example, write access, for example, you have to write the parity of the new data, right. That means anytime you do any write, you have to actually access the parity disk, and therefore, depending on where the data is, there could be a lot of seeks going on all the time. So, to avoid the excess activity on the parity disk, RAID 5 what it does is it rotates the parity. What it means is that you take the first 4 blocks and have the parity on the 5th disk. Then you take for the next block, what you do is you take the first 3 blocks and the last disk block and put it in the 4th disk. Okay. You basically store the parity in a diagonal form. Okay. So, that is what they call it rotated. Okay. RAID 4 does not have rotation. Okay. Basically, there is a dedicated parity disk, and that comes into picture for every parity read, every parity write, it comes into picture. Okay. So, of course, one good thing about RAID 4 is that if you have a different technology medium, like for example flash, okay, and if that is being heavily used, for example, then it may turn out that putting that parity disk in a new technology might help out also. Okay. Some people have proposed those kind of models also. Okay. Whereas RAID 5 may not be able to use it, because they all have to be the homogeneous disks, all of them. They cannot have a separate technology for the parity alone. The good thing about RAID 5 is that it essentially you have 5 disk arms. If you have a 5 disk system, 5 disk arms for parity, okay, not 1 disk arm. Okay. And the reason why this is important is that you might be able to do partial writes. For example, I write only to 2 disks, D1 and D2, then I also have to still update D5, the parity disk. Later I can write D3 and D4, I still have to update D5 in case it is a RAID 4, whereas I can do it onto a different disk in case it is RAID 5, sorry. Okay. So, RAID 5 is common, except that this RAID 5 can be done in hardware or it can be done in software. The good thing about doing it in software is that you are now independent of the disk technology. You can mix disks of different types, different technologies. It can be, for example, who knows, a SATA disk with a SCSI disk, or I can have a SATA disk with a SAS disk. I can do all this if I am doing it in software. Whereas if I do it in hardware, typically the hardware manufacturers, they design it so that all the disks are of the uniform same type of disks. Okay. Because the way the hardware is done, basically connectors and enclosures, all those things typically are decided by various other factors, mechanical and other factors. So, it turns out hardware RAID 5 or RAID 1, if it is done in hardware, it demands uniformity of the disk infrastructure, disks, etc. Whereas when you do it in software, you are basically completely independent of that particular part. But doing it in software, it is very slow. Okay. So, RAID 5 is not really popular done in software. Okay, it is too slow. And also, if you do RAID 5 in hardware, the hardware circuitry can do parity computations and parity, let us say, parity computations quite fast in hardware, okay, because it is mostly XOR. You can only have to do some simple XORing code, XOR logic, which is very easy to do it in hardware. Okay. So normally you will find that RAID 5 is done in hardware, but it makes your you lose flexibility with respect to what kind of disk drives you can use. Okay. It has to be of the same type, usually of the same size also. For example, all should be 1 terabyte, all should be etc. Those kind of things. Okay. So, you also have things like RAID M+N, where you use the RAID M part on the leaf side and RAID N on top of it. So, basically you are doing 2 levels of RAID now. Okay. For example, if I do RAID 10, I basically create multiple RAID 1 volumes, that is mirrored volumes. On top of it, I concatenate them. I get that is basically RAID 10. I can also have things like RAID phi 1. That is what I have is I have multiple RAID phi devices. RAID 1 means I basically also mirror them. Okay. So, I can have all kinds of devices of this kind depending on your requirements. Okay. So, RAID 6.0 for example, that means I have multiple RAID 6, let us say disk systems, multiple RAID 6 systems, and then I am joining them together in a concatenated fashion on the top. Okay. All those things are possible. Okay. So, essentially you can create arbitrary trees of structures now. Okay. So, basically RAID 1 is simple, basically it does mirroring, exact copy is kept. RAID 5 what we are doing? We are taking the data disk at a block level and we are computing the parity and storing it in the parity disk. So, parity is being computed here. In RAID 6, you want to be, because as I mentioned in RAID 5, if there is an error in one disk, the disk will tell you I have made an error and I am not able to supply the information, okay, because there is timeouts and all those kind of things. Okay. There is some way to figure out that the disk is not working. Which disk? I know which disk is not working. Because I know which disk is not working, since I have the parity, I can compute the value of the block on the disk which is not working. I just have to do XOR of everything else, right. So, that is what I am getting by RAID 5. So, it is simple. If there is a single error, I can handle it. The problem with RAID 5 is that I have what is called, if there is an error, I have to read the rest of the disks. What happens if while reading the other disk, I suffer a failure, and that failure is often possible through what is called latent sector errors. That means that I try to read something, at that time the disk comes back and says me I cannot read this stuff. Okay. It is not a whole disk failure, it is just that I am not able to read the sector. I think those of you are familiar with floppies and other kinds of devices will notice that sometimes it reads something, sometimes it does not read some things, right. So, certain parts of the disk may have gone bad, only certain parts. It is able to read other things quite well. Okay. So, not everything is known why it happens, how it happens, but general rule is that it is possible for you to try to read something and you fail reading a particular sector or 2 or 3 sectors nearby. Okay. Rest of it is completely accessible. Okay. So, my problem is that when I am fixing a RAID 5 problem, that is one disk has completely failed, it is catastrophically failed, that means there is no way to revive it. Okay. So, what I am going to do is I am going to read other disks, XOR it and get the value of the block on the disk which has failed completely, and hopefully I have a spare disk and which I am going to transfer it. That is basically my model, recover from the error. But my problem is that while I am reading other things, the other guys can also, if your luck is bad, if you are unlucky, that one of the guys will say I can't read a particular sector. Disk is fine mostly, but one particular sector. So, I cannot recover that portion, that part of the block on the spare disk I cannot recover it. So, this is what is called a 1.5 failure. This is the term that is used, 1.5 failure. Okay. So, this is sufficiently common that many people are not comfortable with that level of protection. That is why I have to do what is called scrubbing. I think we talked about it previously. In scrubbing, what we do is we access every single disk every 20 hours or 40 hours, something like that. You just read it. In case there is a problem when the latent sector occurs, then hopefully at the same time there is no catastrophic failure of a disk at the same time whenever I am doing scrubbing, hopefully. So, therefore, I can actually recover from it, I will rewrite it again, or I will rewrite it into a different place, right. I tried reading it, I am not able to read it. So, I can, the disks have some mechanisms by which they can do what is called revectoring. That is, you are trying to read from block number X, you could not read it, then you are able to recover the value from using RAID 5, the XORing part. Then you write it to another block X prime, which is basically there somewhere as a set of blocks available for revectoring. So, whenever X is mentioned, it actually goes to X prime. Okay. There is some space in the disk for it's what is it called? It's called spare block area, something is called, it's I forgotten the name. Okay. So there is a small set of blocks that are available, so that anytime you have this problem, you can write it to that place, and anytime you ask for x, actually it automatically knows that you're talking about the part which has gone bad, it will go and give you from x prime. Okay. So it will do that. Okay. So because of this, so people who are unhappy about the possibilities like this, these errors like lattice sector, they go for scrubbing. So when you read when you are unable to read from a particular place, use read_fi logic to get at that block and then revector it to a different spare area on the disk itself. Okay. So now you are safe. Okay. But of course, the area is sort of limited. Hopefully, you can at the most probably handle some hundreds or so of blocks which go back. Okay. If that happens more than that, you might have to throw away the disk and get new one. Okay. Okay. Now, those parties who are not comfortable with this, even at this level of this thing, they need to go to RAID 6. So you want to be able to take care of a situation where 2 catastrophic failures take place, not one. In the RAID 5, you handle 1 catastrophic failure, one disk completely died. Okay. There is no response from that. Okay. So here what you do is, in RAID 5 you are doing XOR, right, of the disk blocks and storing it in the parity, right. In the second one, what you do is you use some additional mathematics here. So what you do is, we just say that there is a generator in a field, and you basically what you do is g to the power of 0 is a generator, multiply with the first block d0, and you XOR all these guys together. Okay. Basically, you take the, here basically you start with d0, d1, di, dn minus 1. Here what you do is multiply this with g0, g to the power 0, this g to the power of I, g to the power n minus 1. Okay. And then do the XOR, the same thing you do. Okay. So as usual, if one disk fails, you can still use this parity and survive, just like in RAID 5. If 2 disks fail, suppose it's ith and jth. Okay. So what will happen? I have the XOR of all these guys, right? That's equal to some value, right? And I have value for everybody else, right? So the only thing I don't know is di and dj. So di XOR dj plus everything else is equal to the known value. Therefore, I can get di plus dj equal to some value. So that equation I will get 1. Whereas here also, this also is again XOR. Okay. So I add up all these guys. Now all these values are known, right, except I and j. So I basically have the sum of gi to the power of di, gi d to the power of j to the power of dj will be there. Rest of it is all known. So I finally get this. It turns out, if you choose the appropriate field and whatnot, this is always solvable. You can always get di and dj from this two. All you have to do is substitute, for example, di into this. You can always get dj from it, always. Of course, the trick is basically the generator. So you need to study something about what is called Galois fields to figure out why this works. But I don't want to go into too much detail here. But there is a way to, if you choose your Galois field correct, you will always be able to do it. Always be able to do it. Okay. The only problem with this solution is that this requires, let's say, solution, solving this thing, and also you have to produce this syndrome every time. Anytime some data is modified, you have to come up with a new syndrome. Okay. So it's expensive. Okay. People have figured out how to compute this efficiently using, for example, Intel has got some vector instructions, for example. So there are ways to do all these things efficiently, but it still takes time. So most of the times, if anybody has done RAID 6, it has been done in typically with hardware support. But people also have using software for doing these things. Okay. for example, if you look at NetApp, NetApp has got something similar to RAID 6, and so part of it, I think quite a bit of it is done in software as far as I know there. Okay. So I just want to briefly mention various types of redundancy here. So normally RAID 1 and RAID 5 are what is widely used, RAID 6 for more demanding applications where you cannot handle errors. Okay. So I think I will continue with some of the issues with RAID 5 which ZFS tried to solve. Okay. And also let's look at, I will also look at NetApp, the RAID 4, why that particular thing actually makes sense. Okay. We'll look at it next class.